Welcome back to another deep dive from Peaceful Rooster Experience. Today, we're taking a look at data consistency in distributed systems.
Buckle up.
These systems, they're everywhere. Social media, banking, even just browsing the web.
It's a massive web of interconnected servers, really.
And making sure the data across all those servers is consistent, that's a huge challenge.
A challenge and a half. You could say it's mission critical for things to run smoothly.
Oh, absolutely. Imagine like a banking system where one server thinks you have $100.
And another thinks you've got 1,000.
Then you try to withdraw 500. Chaos.
Pure chaos. Data consistency is the bedrock of trust and reliability in these systems.
So, what makes keeping data consistent so tricky in these distributed systems?
Well, there are three big gremlins in the machine:
Hit me with them.
network latency, concurrent access, and node failures.
Okay, let's break those down, starting with latency.
Right, latency is simply the delay in communication.
So, like sending a signal across the ocean, it takes time.
Exactly. In distributed systems, this means that, one server might have newer information than another, at least for a little bit.
Ah, I see. So things can get out of sync because of these delays.
Precisely. Then you've got concurrent access, which is when multiple users or processes are trying to update the same data at the same time.
Oh, like when two people edit the same document at once.
Exactly. Except on a much, much larger scale.
Yeah, that never ends well. And lastly, node failures.
Right. Servers crash, networks go down, it's inevitable.
I feel personally attacked by that comparison.
Mhm.
So with all these things that can go wrong, how do we even start tackling data consistency?
Well, we have these things called consistency models. They're like sets of rules for how updates are spread across the system.
So kind of like syncing your phone?
Yeah, kind of. Like, do you want it to happen instantly, or is it okay if some things update later as long as they eventually catch up?
Ah, so that's where strong and weak consistency come in.
You got it. Strong consistency means everything is, in perfect sync all the time. Like with bank transactions, you need that accuracy.
Makes sense. You don't want any surprises when you're dealing with money.
Exactly. Weak consistency, on the other hand, allows for some temporary inconsistencies. The idea is that the data will eventually converge. Like with social media feeds, a few out-of-order posts aren't a big deal.
So it's a trade-off, right? Super strict accuracy versus a bit more flexibility.
Precisely. It all depends on the needs of the system.
Now, speaking of trade-offs, what about this CAP theorem?
Ah, yes. The CAP theorem. A fundamental principle of distributed systems.
It sounds kind of ominous.
Well, it states that in a distributed system, you can only guarantee 2 out of 3 things.
Okay, I'm intrigued. What are those 3 things?
Consistency, availability, and partition tolerance.
Okay, so we know consistency. But what about availability and partition tolerance?
Availability means the system is always up and running, responding to requests. And partition tolerance is its ability to keep working even when a network issue splits the system into separate parts.
So it's like if a network cable gets cut.
Yeah, you have to choose between having all the data be the same but potentially unavailable, or having the system work but with possibly outdated information.
So it's like choosing your favorite 2 scoops of ice cream. You can't have them all.
That's a good analogy. In the real world, though, network issues happen, so most systems end up sacrificing strong consistency in favor of availability and resilience.
Right, you need the system to keep working even if things get a bit out of sync temporarily.
Exactly. It's a delicate balancing act.
Okay, so we understand that things can get messy, even with these consistency models. But what are some of the common culprits that can cause data inconsistency?
Well, aside from those big 3, there's network partitions, concurrent writes, hardware failures, buggy code, even human error.
Oh, right. Human error, the ever-present gremlin.
It's a fact of life, unfortunately. Even with the best intentions, things can still go wrong.
So it seems like achieving data consistency is like playing a never-ending game of whack-a-mole with these gremlins.
In a way, it is. But thankfully, we have some powerful tools at our disposal to combat these challenges,
Like what?
like distributed consensus algorithms.
Okay, those sound intense. What are they?
Think of them as sophisticated voting systems for computers. They help servers agree on the correct data, even when things are going haywire. Algorithms like Paxos and Raft are the heavy hitters in this space.
So it's like a digital democracy for servers, making sure everyone's voice is heard.
Exactly. It's a powerful way to achieve consensus in a distributed environment.
But what happens when some of these voters are MIA because of network issues?
That's where quorums come in.
Quorums.
A quorum is the minimum number of nodes that need to agree before a decision is considered valid.
So even if a few servers are down, we can still move forward as long as enough of the others are in agreement.
You got it. Quorums provide a way to maintain consistency and make progress even in the face of failures.
Clever. But achieving this strong consistency across the board, that's got to come with some drawbacks, right?
You're absolutely right. It can be a real performance killer. Imagine trying to get everyone in a giant stadium to agree on something simultaneously. It's going to take time and effort.
So strong consistency is like trying to herd cats.
Pretty much. It can also be incredibly complex to design and manage systems that can handle this level of synchronization.
So it's a trade-off. You have to weigh the need for strong consistency against other factors like speed, complexity, and cost.
Exactly. There's no one-size-fits-all solution. It all depends on the specific needs of the application.
Okay, so let's shift gears for a second and talk about the different types of databases out there. Don't they handle consistency differently?
Absolutely. We have relational databases, the old guard, known for their ACID properties,
ACD properties.
atomicity, consistency, isolation, durability. These properties ensure that transactions are processed reliably and consistently.
So relational databases are like the Fort Knox of data storage. Super secure and strict.
Exactly. Then you have NoSQL databases. They prioritize speed and scale, but they might be a bit more relaxed on the consistency front.
So it's like choosing between a bank vault and a super fast delivery service for your data.
That's a good way to put it. And then you have NewSQL databases, which are trying to combine the best of both worlds.
So they're like the hybrid vehicles of the database world.
You could say that.
So no matter what type of database you choose, you're bound to encounter conflicts in a busy system, right?
Conflicts are inevitable, especially in a distributed system where multiple processes are constantly vying for the same data.
It sounds like a digital battle royale.
It can be, but thankfully we have some strategies for resolving these conflicts.
Okay, like what?
One common approach is last write wins, where the most recent update simply overrides any previous ones.
So kind of like a digital game of King of the Hill.
Exactly. It's a simple solution but can lead to data loss.
Right, because you might be overwriting valuable information. What about when you need a more nuanced approach?
Yeah, and we can use timestamps and vector clocks. They're like detailed timelines of events helping us track who changed what and when.
So instead of just blindly overwriting data, we can trace back the history of changes and make informed decisions about which updates should prevail.
Precisely.
Okay, that makes sense. But what about those CRDTs you mentioned earlier? Those sounded like pure magic to me.
CRDTs, or conflict-free replicated data types, are special data structures designed to handle concurrent updates without conflicts.
So it's like having a Google Doc where multiple people can edit simultaneously without ever getting those annoying merge conflicts.
Exactly. CRDTs are a fascinating area of research, and they hold a lot of promise for building highly concurrent and consistent systems.
Wow. It sounds like there's a whole world of techniques for managing data consistency.
There is, and we've only just scratched the surface.
Well, that's all the time we have for the first part of our deep dive into data consistency. We've covered a lot of ground, from the basic challenges to some of the key techniques for keeping things in sync.
But we're not done yet.
Stay tuned for the next part, where we'll explore real-world examples of how these concepts are being applied in practice.
It's going to be a wild ride. Welcome back to our deep dive.
So last time we talked about the challenges of data consistency.
The gremlins.
Yeah. But how does all that theoretical stuff actually play out in the real world?
Well, let's say you're trying to buy, I don't know, the latest gadget online.
Ooh, I love new gadgets.
So you add it to your cart, hit purchase, and boom, the site crashes.
Ugh, the worst.
And then when you reload, it's like your shopping spree never even happened.
Okay, that's more than just frustrating. That's a sign that something went wrong with consistency somewhere.
Yeah, it happens. But honestly, these kinds of failures are pretty rare these days.
I guess that's true. I mean, most websites seem to work fine.
Right, and that's because of all the clever engineering that goes into preventing these issues. But the potential for chaos, it's always lurking.
So, like a ticking time bomb.
Kind of, yeah. But the severity of the consequences, it really depends on the system and the data it's handling.
Okay, so, like with social media, a few duplicate posts might be annoying.
Right. But they won't break the whole experience.
But imagine if, like, every time someone liked your post, it showed up 100 times.
Exactly. Weak consistency works for social feeds because the stakes are lower, But even there, too much inconsistency and it's game over.
So it's about choosing the right level of consistency for the job, right?
Precisely. And then you have systems where even the tiniest inconsistency can be
Like
catastrophic.
air traffic control or something.
Exactly. Or think about online gaming.
Ooh, yeah. I'm a gamer. I know all about lag.
Right. Lag is the bane of any online gamer's existence.
It can mean the difference between virtual life and death.
No kidding. And online gaming is a perfect example of how those C-key theorem trade-offs play out in the real world. You've got dozens of players interacting in real time. Network issues are bound to happen.
Always at the worst possible moment, too.
Right. So do you halt the entire game for everyone if one player's connection blips just to ensure perfect consistency?
That would be infuriating.
It would. Or do you allow a bit of lag, some temporary inconsistencies, to keep the majority of players in the action?
I mean, as a gamer, I'd rather have a little lag than have the whole game freeze up.
Exactly. So it's a constant balancing act.
Between consistency and, what was it again?
Availability and
Yeah.
partition tolerance. Remember, you can only pick two.
Right. The CAP theorem. But let's go back to that online shopping cart example.
Sure.
How do they make sure that most of the time our purchases go through without a hitch?
Well, remember those distributed consensus algorithms we talked about?
Paxos and Raft guys.
Those are the ones. They play a huge role in keeping things consistent behind the scenes. They act like super reliable messengers, making sure all the servers agree on the state of your cart, your payment information, everything.
So it's like a perfectly choreographed dance with each server knowing exactly what to do.
You could say that.
But what if one of those servers, like, trips and falls?
That's where those trusty quorums come back into play. Instead of needing all the servers to agree, we can say, hey, if a majority are on the same page, we're good to go.
Ah, so it's like having a backup dancer ready to step in if the lead dancer twists an ankle.
Exactly. That's what makes these systems so resilient.
So it's a combination of clever algorithms and fault tolerance mechanisms that keep our digital lives from imploding.
Pretty much. Now let's talk a bit more about how different databases handle all of this.
Okay, yeah. We touched on that briefly last time.
Right. So relational databases with their strict acity properties, they're like the perfectionists of the data world. Every transaction has to be completed fully or not at all. No room for error.
So they're kind of inflexible.
In a way, yes. But that rigidity is also their strength. It ensures data integrity. But it can come at a cost, especially when you need to scale up.
Right. And that's where NoSQL databases come in, right?
Exactly. NoSQL databases, they're more relaxed about consistency. They prioritize speed and flexibility.
So it's trade-off again.
Always. You have to choose the right tool for the job.
Okay, so relational databases are like fine dining. Everything's perfect, but it takes time. And NoSQL is like fast food, quick and easy, but maybe not as elegant.
I like that analogy. And then you have those NewSQL databases which are trying to bridge the gap.
Right. They want the best of both worlds.
Exactly. They're like food trucks of the database world, serving up gourmet meals at lightning speed.
Okay, I'm hungry now.
Yeah.
But seriously, no matter what type of database you choose, you're bound to encounter conflicts.
Right. Conflicts are like a fact of life in distributed systems, especially when you have lots of processes accessing and modifying data concurrently.
So it's like a digital game of musical chairs where the chairs are constantly disappearing and reappearing.
Something like that, yeah.
So how do we deal with these conflicts? We talked about last right wins before, but that seems kind of crude.
It is a bit simplistic, and it can lead to data loss. That's why we have more sophisticated techniques like using timestamps and vector clocks.
Okay, remind me again how those work.
Sure. Imagine you're trying to reconstruct the events of a car accident. You'd want to interview witnesses, analyze skid marks, and piece together a timeline of what happened.
Right. To figure out who's at fault.
Exactly. Timestamps and vector clocks, they're like the forensic tools we use in distributed systems to understand the sequence of events and resolve conflicts in a way that preserves data integrity.
So instead of just assuming the last car through the intersection was in the right, we can actually look at the evidence and figure out what really happened.
Exactly.
Okay, that makes a lot more sense. But what about those magical CRDTs? Do they somehow prevent these accidents from happening in the first place?
CRDTs are like self-driving cars. They're designed to navigate the complexities of concurrent updates without collisions. They use special data structures that allow independent modifications to be merged seamlessly, even when they happen simultaneously.
So instead of relying on external mechanisms to manage conflicts, the data itself is inherently designed to avoid them.
That's the idea. CRDTs are a fascinating area of research, and they hold a lot of promise for building highly concurrent and consistent systems.
Cool. But even with all these fancy tools, designing systems that can withstand those network partitions, those digital walls we talked about, that seems like a real nightmare.
It's definitely one of the toughest challenges in distributed systems.
So how do we deal with those?
Well, we have those two old faithfuls, two-phase commit and distributed locking. They help us manage updates across those partitions, ensuring consistency even when communication is disrupted.
So 2PC is like having a super organized border patrol, carefully coordinating the flow of data across those digital borders.
Yeah, that's a good way to think about it. And distributed locking is like having checkpoints that prevent unauthorized access to sensitive areas.
Makes sense. But those approaches can be pretty heavy-handed, right?
They can be. That's why we also have quorum-based replication, which uses those trusty quorums we talked about earlier to make things more efficient.
So it's like having a distributed voting system that can operate even when parts of the network are cut off.
You got it. Quorums are a powerful tool for achieving fault tolerance and consistency.
Okay, so we've got all these different consistency models, algorithms, and techniques. How do we know which one to choose for a specific application? It's like trying to navigate a maze.
It can be overwhelming, but the key is to understand the trade-offs involved and prioritize what matters most for your particular needs.
So do you need absolute consistency, even if it means sacrificing performance?
Or can you tolerate some inconsistency in exchange for greater speed and flexibility? Those are the questions you need to ask yourself.
It's a balancing act, like juggling chainsaws while riding a unicycle.
That's one way to put it. And the right answer will depend on a variety of factors, like the sensitivity of your data, the frequency of updates, and your overall performance requirements.
So there's no one-size-fits-all solution.
Nope. Every application is different, and you need to choose the approach that best fits your needs.
Okay, I think I'm starting to get the hang of this.
Yeah.
But it's clear that data consistency is a complex and nuanced topic.
It definitely is. But it's also a fascinating one.
Well, we've covered a lot of ground in this second part of our deep dive. We've seen how data consistency plays out in real-world scenarios, from online shopping carts to video games.
And we've explored some of the techniques used to achieve consistency, like consensus algorithms, quorums, and conflict resolution mechanisms.
But the journey's not over yet. Stay tuned for the final part of our data consistency adventure.
Where we'll explore the cutting edge of this field and the challenges that lie ahead.
And we're back for the grand finale of our data consistency saga.
The climax, where we face the ultimate bosses of distributed systems.
Last time, we talked about real-world examples, right? Like how consistency plays out in things like online shopping.
Right. But now we're going to crank things up a notch.
Okay, so what's on the menu for today?
Today, we're talking about the trends that are pushing the boundaries of data consistency. Things like geo-replication, edge computing, serverless architectures, microservices.
Those are some big words.
They are. But there are also some pretty big deals in the world of technology. They're all about making systems more distributed, more complex, and, you guessed it, more challenging to keep consistent.
Okay, so let's start with geo-replication. Isn't that just a fancy way of saying the cloud?
Well, sort of. The cloud is basically just someone else's computers, right?
Right.
But geo-replication takes it a step further. It's about making copies of your data and storing them in multiple data centers, often on different continents.
So, like, if one data center gets hit by an earthquake, the others can take over.
Exactly. It's all about redundancy and resilience. If one part of the system goes down, the rest can keep running.
Okay, that makes sense. But wouldn't sending data across the globe introduce a ton of latency? You know, those delays we talked about earlier.
You're absolutely right. That's the trade-off. You gain resilience, but you also make it harder to maintain consistency.
Because the data's so spread out.
Right. Imagine trying to keep two clocks perfectly synchronized when one's in London and the other's in Tokyo. Even the speed of light isn't fast enough to eliminate all the discrepancies.
So how do you deal with that?
It requires some pretty sophisticated techniques. We're talking about algorithms that can track the order of events across vast distances, taking into account things like network delays and server clock differences. It's like trying to reconstruct a conversation that happened between people scattered across time zones. You need to make sure you're hearing everyone's side of the story in the right order.
Okay, that sounds complicated.
It is, but it's also incredibly important.
Right, because if you get the order wrong, things can get messed up pretty quickly.
Exactly. So geo-replication is all about achieving ultimate resilience, even at the cost of some added complexity.
Okay, I think I'm starting to get it. But what about edge computing? Isn't that all about speed?
It is. The idea is to bring computation closer to the user.
So like if I'm watching a movie on my phone, the data is processed on a server that's closer to me.
Exactly. Instead of sending all that data from a central server, which could be thousands of miles away, you process it on a server that's just down the street.
So less buffering, faster downloads, happier users.
Precisely. But it also introduces some new challenges for data consistency.
How so?
Well, now you have data being updated and processed in multiple locations. You need to make sure that those changes are synchronized, that the central data center remains the source of truth, but without introducing so much latency that you negate the benefits of edge computing in the first place.
So it's like trying to coordinate a team of chefs working on the same dish, but they're scattered across different kitchens, and some of them have faster ovens than others.
That's a great analogy.
Thanks. I try. But speaking of different ways to cook up data, what about serverless architectures? Those seem to be all the rage these days.
Serverless computing is a fascinating concept. It's like having a magical kitchen where dishes cook themselves.
Sounds amazing. Sign me up.
Right. Developers write code without having to worry about the underlying infrastructure. But this magic comes with its own set of consistency challenges.
Like what?
Well, in a serverless world, data is typically stored in external services like databases or object storage.
Okay.
But the challenge is that serverless functions, they're ephemeral. They spin up, do their job, and then vanish.
So they're like little gated ninjas popping in and out of existence.
Exactly, and that makes it tricky to maintain a consistent view of data across different function invocations. It's like having a team of temporary workers who come in, do a specific task, and then disappear without sharing their notes.
So how do you keep track of everything?
It requires a different approach to data management. You need to ensure that data is persisted correctly, that any changes made by one function are visible to the next, and that the state of your application is preserved across these transient executions.
So it's a whole new set of rules for the serverless game.
You could say that.
Okay, so we've covered geo-replication, edge computing, and serverless architectures. What's next?
Next up, we have microservices.
Ah, yes. The trend of breaking down big applications into tiny little pieces.
Exactly. Microservices are like having a team of specialists working on a complex project. Each service is responsible for a specific domain, which allows for greater agility and flexibility.
So it's like having different departments in a company, each with its own way of doing things.
Right. But it also introduces complexity, especially when it comes to data consistency.
Because now you have to make sure all these different services are playing nicely together.
Exactly. You need to ensure that data is synchronized across services, that any changes made in one service are reflected correctly in others, and that you avoid creating a tangled mess of data dependencies. It's like trying to manage a global supply chain, where each step in the process needs to be perfectly coordinated to avoid delays and disruptions.
And just when we thought things couldn't get any more complicated, we have the Internet of Things, or IoT, exploding onto the scene.
Ah, yes, the IoT. A data consistency nightmare, some might say.
How so?
Well, we're talking about billions of devices, sensors, actuators, smart appliances, you name it all, generating data at an unprecedented rate.
It's like trying to drink from a fire hose of information.
Exactly, and keeping all that data consistent is a Herculean task.
So where do you even begin?
You need new approaches to data synchronization, edge processing, and distributed data management. You need to be able to handle massive volumes of data coming from diverse sources, often with limited bandwidth and unreliable connectivity. It's like trying to conduct an orchestra of millions of instruments, each playing its own tune and somehow making it all sound harmonious.
Okay, my brain is officially fried.
I don't blame you. It's a lot to take in.
So what's the key takeaway for our listeners? What should they be thinking about as they try to make sense of all this?
I think the most important thing to remember is that data consistency is not just a technical issue, it's a business critical issue. Meaning that inconsistent data can lead to wrong decisions, lost revenue, damaged reputations, all sorts of bad things. So it's essential to understand the different consistency models, the trade-offs involved, and the techniques available to ensure that your data is accurate, reliable, and trustworthy.
And it's about being proactive, right? Like not just waiting for things to break before you take action.
Exactly. You need to be constantly monitoring your systems, looking for potential issues, and making adjustments as needed. The world of data consistency is a dynamic and ever-changing landscape.
Will said. And on that note, I think it's time to wrap things up.
I agree.
We've covered a lot of ground in this deep dive, from the fundamental concepts to the latest trends that are shaping the future of data consistency.
It's been a wild ride.
It has. But hopefully our listeners now have a better understanding of the challenges involved and the tools and techniques available to overcome them.
That's the goal.
And as always, if you want to learn more about this fascinating topic, there are tons of resources available online. Just make sure you're getting your information from a reliable source.
Good advice.
And with that, I think it's time to bid our listeners farewell.
Until next time.
From all of us here at Peaceful Rooster Experience, thanks for joining us on this deep dive into the world of data consistency. We'll catch you on the next one.